This podcast is presented by hannovermesse, your leading event for industrial AI.
Hello everybody and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber and it's a pleasure to talk to Professor Dr. Johannes Brandstetter. Welcome to the podcast.
Hello, thanks for having me.
Today we are going to talk about simulation and AI, and you will also presenting this topic at our event AI in the Alps. We are really looking forward, but before we start talking about technology, AI and simulation, please introduce yourself briefly to the listeners, Johannes.
Yeah, hello everyone. So my background is both physics, machine learning, industry and university. I've spent 3 marvelous years in Amsterdam, first at the University of Amsterdam and then at Microsoft Research, where we have had a super good team and we did weather modeling at scale. And this weather modeling was also what motivated me to look at simulation at scale and at large scale simulation. And with that knowledge in the back of my head, I moved back to university, looking into the Austrian and German industry, where we have a lot of nice companies like Trumpf, Bosch, Zeiss, and many, many more. And what all of these companies have at their core is that they are based on industrial processes. And this is where I think we can move something, we can apply AI, and this is exactly what I want to do here in Austria.
This morning I sent you a news item to illustrate why AI and simulation is so crucial, I think. And I have one quote: "The entire learning process takes just 18 seconds. And the researcher used the GPU of a MacBook to run a very fast multi-rotor dynamic simulator. And this takes it possible to simulate 5 months of flight per second." Is this the future for simulation and AI?
Yes, I very much believe so. It's a great article. I think AI makes it possible to simulate stuff which otherwise we cannot do, because it's much, much faster and it scales much, much better. Of course, we can only be as good as the simulation is, because this is where we get the data from. But I think there is a way around, because what AI has told us, what large language models have told us, we can learn from many, many data. And there is so much data lying around that we just need to harvest this data and build into one model which basically models or can be fine-tuned to the simulation at hand which we need.
So can you please explain a little bit simulation and AI? We still have very good simulation tools and we have good simulations in the industrial process. And on the other side, we have AI and deep learning. Where does it come together, both worlds?
Yeah, first of all, I have to say numerical methods, they date back to Gauss and they are like super sharp to an extent where it's really, really hard to see them as a competitor which needs to be beaten. So I don't think that these simulations as they are, which can be from writing numerical solvers to the Navier-Stokes equation to some industrialized processes which follow a certain protocol. So all these different kind of simulations, they are of course on the other hand, and on the one hand is the new tools of AI. How they come together, simply that what is simulation doing? It's a time series most of the time. So you have some process which runs over time, like a computational fluid dynamics, some airplane, some car in the wind tunnel, or many, many other processes. And those processes can, of course, be modeled by neural networks which learn to predict forward in time. And this is exactly where
But this is not new, right?
This is not new, no. But what is new is that we can apply them now to such simulations, because we know how to build large models, we know how to use these large meshes and many particle systems, and we have enough compute also from numerics to get the data which we need.
So you still need the simulation, right?
Simulation is the core of everything, yes.
So I need a simulation of a process, and what do you do then with this data?
Yeah, the core idea is always at some point build an AI model which replaces the simulation.
Why? Why should it be replaced?
That's a good question, because it is, as I said in the beginning, it is faster, much, much faster, and that allows us first either to use it for production, but also to test different parameters. Second of all, it can generalize, because it can be run with different settings. And third of all, it can run on a sparser grids and extrapolate just better. But off the core of all of this is simulating the simulation data. So we need to have this data to generate something where we can learn from.
Let's start with the first point, make it faster. How do you do that?
That is very simple because AI-driven models are in inference very fast. The numerical models, they are constrained by something which is called Courant-Levy-Friedrich condition, which means the step you take in time is conditioned on the step you take in space. And these steps are usually very, very small, especially in 3 dimensions. And that takes a long, long time to run forward passes. So usually we all have no processes which days, weeks to simulate. And they are like super precise, but they take a long time. And this is where AI can be a game-changing factor, because suddenly we can simulate things for which we would need to wait weeks. We can simulate much, much faster.
Mm-hmm. But you are not able to simulate anything what is not seen before, right? Or can you generalize?
I mean, that is the big question, the big goal. If we have enough data and if we can train models, then of course we can generalize across parameters, across meshes, across boundary conditions and so on and so forth. And this gives us the opportunity to study phenomena, to study circumstances just by running different AI solvers forward and checking how these comply. So in that sense, I would say, yes, we can study new phenomena, but of course all of them have to be in the range of what we've known from the data.
What do you see? What kind of new simulations can we achieve with this technology?
For example, if we stress again cars, and if you have a wind tunnel, and we try to find some optimal settings that fit.
This was Günther Klambauer, by the way.
So if you have this wind tunnel and we want to fit, or we want to understand what's the best aerodynamics of the car, we can run a certain setup forward and we look at the turbulences and so on and so forth. And then we change some things slightly and run the new setup. It takes us seconds. And with these setups, we get a feeling how best to modify the car to get the best possible design. And potentially these design then we use with a standard numerical method to optimize and so on and so forth.
So test less.
Exactly.
But I think, for example, wind tunnel testing and the big automotive companies are already going this way to try out to work with AI simulations. Or am I wrong?
Yes, definitely, 100%.
What is so new with your approach?
I wouldn't say it's new. I just want to apply it to other processes than just computational fluid dynamics in wind tunnels. I think this can be applied to many discrete element methods, finite difference solvers, and whatever we have here lying around and whatever industrial processes we have.
What do you have in mind? What is your idea?
So the first idea or the first big project we are doing is with discrete element methods. So these are particle-based methods where you don't know the underlying equations. You just don't know how particles interact with each other. And with these methods, you can simulate large-scale systems, for example, rotating drums or whatever industrial processes you have. That takes a lot of compute, is not doable in real time, so you have to wait. Of course, there are processes which try to optimize, and this is an ideal test bed for AI because you have some advantages. You can learn the general dynamics, you can learn to understand how things work. And this is also one of the collaborations we have in mind to really scale up.
Okay, but I see here no robot, no machine. You have no domain-specific knowledge about these processes. Don't you need this to run simulations based on AI, this domain-specific knowledge?
So we have experts. So of course, talking here with some of the best people in discrete element methods, which exactly know what are the open problems, what need to be the problems to tackle. And on the other hand, we have the AI experts who know how to scale, how to use compute, how to use abundance of data to make this work. And we take it from there.
Okay. You mentioned to generalize simulation or to generalize simulations. What does it mean to generalize this simulation? Can I take a weather simulation and use it in the industrial sector?
That is a far stretch, but
you mentioned that.
Yes, I love to do that. But let's first say that the first simple generalization is going back to the wind tunnel because this is the easiest example. And now we want to have it to work for different velocities of the wind. So it should work for 50 kilometers as much as it works for 150 kilometers. And everything in between is basically generalization. But that's a very simple generalization, and that is not giving us a lot. But I argue that all of the that the physics which is around us is very similar. There's a few terms. There's a convective term, there's a diffusive term, and some other terms, but all of these terms are very similar. So why not use the abundance of the data we have from weather, from computational fluid dynamics, and from many other of these domains to build very, very large models which can then be fine-tuned to these tasks at hand.
This is the idea, to build a simulation foundation model or something.
Of course, yes.
And then the company is using this big foundation model, is only taking one part of it, right?
Taking the model and fine-tuning it to the task they need, yeah.
How realistic is that?
I come from weather modeling, where I think we went pretty far. We are now looking at computational fluid dynamics in 2 and of course 3-dimension, discrete element methods in 3-dimension. We're already using different kind of data. So data which is described by a grid, by moving mesh, data which is described by moving particles. We all inject those to one model and we can scale up quite reasonable. And of course the litmus test is now to apply then that to real world problems. But I think we are going pretty fast and pretty far. It will take us a few more months, but we are getting there.
Okay. Can you explain us a little bit how to apply then this approach to real world use cases?
Yeah, so the first real world use case will be, as I said already, discrete element methods of some particular industrial problems. The second use case will be some well-known 3D computational fluid models with turbulence included. And I wouldn't say toy, but these are the problems we need to solve. And if we're able to solve those, we can go further, we can go bigger, we can collect more data, and we can try to tackle more challenging problems. But I would say that we first need to establish an understanding of how we can beat numerics, how we can get an advantage, and how we can advance industry here.
Okay. What is your feedback from the industrial sector when you present your ideas?
So there is, I would say, mixed feedback. I talk a lot with experts from numerics. Many of those have really understood the need to do something revolutionary, which AI can provide if used correctly. But on the other hand, this is, as I said already, numeric simulation date back to Gauss. So why should these neural networks change things?
But it works, yeah.
Yes, but to make it work is a hard. So I wouldn't say that it will work from one day to another. And I play around with this for quite some time now. So it's harder than we think. But it also took some time to get large language models to work. So we are getting there.
So you're based on transformer? No. What is under the hook?
In the end, I wouldn't say so much the model, if it's in transformer or something else, but I think that the main and important ingredient is that we model something in what is called the latent space, a space which has much fewer dimensions than the space the dynamics are simulated with standard numerical solvers, simply because if we think of a mesh of 100,000 or a million of points, it's just untractable to do every step on this grid. We need a space where all this dynamics is formed, which is much, much smaller. And this is, I think, the core idea of that all.
What is your time horizon on this? Now, you mentioned we are starting to apply, we are doing research on that. When will industrial companies, from your point of view, will use AI-based simulation on a broader scale?
That is a very good question. I would say that's within the next 2 to 3 years that there is coming a big revolution. Of course, I want Europe and Germany to be part of this revolution.
What is so special, this revolution?
I think that if simulation is really augmented with AI, we can simulate processes much, much, much faster, and that will allow us to build new products, to explore the search space much, much faster, and that's just the productivity is going up.
I know companies which do not know what's happening in their process. For example, when you produce very special glass or something, they are not able to say what's happening there in this process. They are not able to simulate this.
Yes, and that is the second point. I know it sounds very strange, but also to somehow get a better understanding of processes, because we can play around with parameters, we can play around with understandings. But of course, this is not replacing numeric simulation, this is augmenting it, this is helping, and only these tools together will make a revolution. I don't know how big this revolution, but it is coming, and it's coming very fast. And I know that from looking at the US, from looking at people doing there in their startups.
So they're working on products?
Yes. There's a lot of simulation-based startups, especially in Bay Area and Seattle and so on. And my former colleagues, 2 of them work in such startups, and I want to have that in Europe as well.
You're planning to build a product out of this simulation research?
So I want to provide the needs for building these products. I want to equip our companies, our people here to build these products. And yes, I hope products are coming out from Europe.
When you think about your project and your research, what is still not solved?
I think what is not solved is the scaling. So in large language model, companies have figured out how to scale these big models. But for many of these simulators to work really, really well, to bring really a game changer, we need to scale them as well, because only that unleashes the power of AI. But how to scale is a bit harder than for large language models, because how to get so many data, how to train across so many different modalities of data, and of course, where to get this compute from. So that is the big challenge, how we can scale these simulations.
Is it an option for Europe to focus on this topic simulation instead of going into large language models and follow this road to large language model and better focus on simulation topics?
I would love to, but I say that everything is intertwined. So large language models is the driving force of AI. That's also why I'm
in the moment.
Yes, in the moment, but it was also the last years. And I'm very happy to have it like that. And I'm very happy to have like people like Sepp sitting next to me with whom I can talk about large language models, because whatever is going to be there will be in other parts in 1-2 years later. And especially for large language model and simulation, it's very clear both of them are autoaggressive. So in large language models, you predict the next tokens again and again and again. In simulation, you predict the next states again and again and again. So things which work in large language models are in one way or the other will work in simulations. I'm also very happy to see this trend towards multimodality, because this is exactly what I'm saying. In simulation, we have many different kind of data, and we need to...
How do you handle that?
So I would say there's no way that Europe is not jumping really on this large language model train, which it is doing now, happily, but everything will profit and benefit from that.
You mentioned these different types of data. Can you please once again describe how you handle this? How does it come together?
Yeah, that's a bit technical, but in the end, you can really think of it as you have in text data and image data. I mean, it's also very, very abstract. But if you find the right way of how to describe the data, you find the right way of put it into a representation, which then can be handled by one model. And the different data we have in simulations are what is called Eulerian and Lagrangian. Eulerian is a mesh, so you describe everything as a mesh. Imagine your car, which has different points, and then all of these points are interconnected such that the shape of the car arises. And then you have Lagrangian data, which are particles which fly around and which are used to simulate like different kinds of fluids and different problems of fluids. But in the end, these Eulerian Lagrangian data are they look different, but they're very similar. So of course you can put a point basically as a representation and then map them to some common space. And that's exactly what we are doing.
Okay. So at the end, I want to ask you, what is your field of research, simulation and AI? How do you come to this topic?
I think it's intrinsic fascination of seeing what is possible. I was really, really struck by the sheer power of what you can do in weather modeling. Also very much inspired by what is going on in large language models and computer vision. And I still have a part of my heart is a physicist, and just trying to write these numerical solvers by yourself and trying to fine-tune them gives you an understanding of what could be possible. And this is driving and fascinating me.
What are your next steps? So you also work for NXAI here in Linz. It's not all about XLSDM, it's also about simulation. What are your next steps?
Yes, we have in NXAI, we have a simulation group. We have some papers in the pipeline, which we will put out soon. And based on these methods which we're developing, we will try here to really, really scale up. As I said already, the next big task to tackle are discrete element method simulation. We have some experts in Linz. We know some real world problems. We will use this definitely to showcase what is possible and take it from there.
Thank you. It was a pleasure.
Thanks a lot.